Have you ever dreamt about testing all your requirements at the same time? Always. With the SAGA tool, this dream is one step closer to become true. I am Daniel Flemström and I have developed this tool together with RISE, Scania and Bombardier. So why do we need another tool for testing? Well, the usual way of testing is described in this figure. Typically, we have a set of stimulus that we put to the system under test. We wait for a response and we check once that the requirements are met. Based on this, we create a verdict if it's pass or fail or if we couldn't run the test at all. And as you can see, we only check each requirement once. But what if anything happens after we check the requirement? Or before we check the requirement? Well, these faults will simply be missed by this method. But what if we could check each requirement all the time? So this is where the SAGA tool comes into play. So the SAGA tool allows you to express your requirements in a way that they could be checked continuously over the whole log sequence. In this demo, I will show you how to take the requirements in, for example, a door repository and express them in a language that allows us to evaluate them continuously using the interactive editor in the SAGA tool. This interactive editor is capable of reading old signal logs, which makes it much more simple to complete the expressions. And now, before going into the demonstration of the actual tool, let's just take a brief look at how a requirement could look like in the doors repository. There are, of course, many ways of describing requirements, but in our case, requirements are described in natural language and also in a semi-formal format. And as we can see in this picture, all requirements have an identification number. It also has an overall description of the requirement. In this case, it concerns the cab doors. And as long as any cab door is not closed and locked, start inhibit should be set. And this part, input and output, shows the expected input and the expected output of the system. And this is the part that we will translate to an executable requirement. So when we are translating the requirements, we use the tiers editor as this. And usually I start with adding the requirement as in the original text as a comment. So let's start with describing when we want to check this requirement. And that in this case is very thoroughly described in the input clauses here. So we need to check which signals we use to describe that the cab doors are closed and locked. And this equals false means that, okay, they should not be closed and locked. So as you may know, in a real train, all the signals have horrifying names, which are not very easy to read. And that's why we have defined abstract signals for each release. And we can actually search for them. This text goes right into the filter. And we see that, okay, we can use these definitions here. So we need a keyword that's called while. So you also need to know that we have two cabs, A1 and A2. So according to requirements, as long as the cab door in A1 is false, or the cab door in A2 is false, we want to check the requirement. And as I said earlier, this is an interactive editor. And that means that anytime when I have a valid expression here, I can press Ctrl and Enter, and the expression will be evaluated using the loaded log file. And all the sub-expressions in this will show up here as plots. So these are the underlying signals for these expressions, and the gray marking here shows where we actually check the requirement. So let's also add the actual check, and this we do with the shall keyword, and this part describes what we expect in those gray areas. And again, we can go to the definitions here and we search for inhibit reason cab door in any order. Cab door in, you see, this seems quite, this one, yes. And we can also try to evaluate it. And we can go down here to see that now we have the gray areas here. It's for each, it's an overlay for each of these plots, but we also have a green part here. So that's quite nice. But also when the expressions get more difficult, it's also nice to be able to vary these signals a little bit to see that we get a pass when we expect and get a false when we expect that. And to that we have a signal editor, and we can actually right click and choose use edit used signals. This means that all the signals, all the underlying signals here are actually added to an editable view. So we can actually change these and see how the expression is evaluated if we change these signals. Also, this means that we can experiment with this, but also we can, as a requirement engineer, I can create examples where I say this is how it looks like when it fails, and this is also a couple of situations where it should pass. And as a requirement engineer, you would probably not use these low-level signals, but you could actually create signals with this name directly. And then the test engineer has a job to discover what physical signals you need to determine if the cab doors are closed and locked. Given this, we can actually evaluate this on another file. So let's do this. So now I have loaded another log file for these expressions, and it's loading like this. And you see a list of these new signals. We go back to the editor and we evaluate the expression here. And now we can also see that we have two periods in gray where we check the requirements. Within these periods, we have two periods with pass and one with fail. And this is also what's new with this method, that you can have both passes and fails. So we need to look at this fail to understand why and why it's failing. So if we select that one, that region would be put in the middle. We can zoom in a bit, can zoom in a little bit more, and we see this is the problematic region. We can zoom in even more. What I usually do is that I ask for all the signals that have changed during this time. So I select that one, and then I will get all those signals that have changed. So this one obviously has nothing to do with it. This one is suspicious and that one is suspicious for that one. In this case, I know that this is a natural latency in the system, because when you write expressions this way, it's very exact. So we can actually add a little bit of slack. So I say, okay, let's allow a slack of 1 second. And now you see that the red region is gone and we have only green, as in pass, for this. You can also see that you have a guard here that has only 1 green. This guard has also only 1 green, no reds whatsoever. Yeah, so that's about it.